So when it comes to how you actually present this descriptive analysis you've been doing, you have to consider different kinds of rules for different forms of presentation. Like when it comes to how you present your descriptive statistics in writing, while typically you should do that. Most research reports go into a lot of detail in the writing as to what the means and standard deviations were and things like that. And this is especially the case if you have a small amount of results to report. So if you're just reporting a few different means, just put them in the writing, and that's perfectly fine. Now, when you do put the means and standard deviations and other descriptive statistics in your writing, you typically want to write out the terms mean and standard deviation. But there are some cases where you might, decide it makes more sense to abbreviate. And in those cases, you would use the symbol of a capital M for the mean and a capital SD for the standard deviation. And those kinds of symbols would go into like a little parentheses. So let me give you an example. You could write in your results section something like this. The mean age of the participants was 22.43 years with a standard deviation of 2.34. So that's a very common way to write out this kind of stuff in a results section. But you could also use that other format I mentioned where you put the mean and standard deviation in parentheses. And personally, I think this looks a lot nicer because now you can just describe the data in more common terms, more relatable terms. Like you can see here it says, among the low self-esteem participants, those in a negative mood expressed stronger intentions to have unprotected sex than those in a positive mood. So if you're the reader and you don't particularly care about the details, you can just skip over those little parenthetical statements. But if you want to know the exact difference that this author is describing, then you have the option to check that out. So expressing your descriptive statistics in the writing is a very common thing. You see it in almost every research report. But something else that's just as common, especially when it comes to presenting your research to other people, like different kinds of people that aren't in your particular profession, your field of research. Something that works very commonly in those situations is visualizing the data with a graph. And this is also very commonly done when you have a large amount of data to report. So APA style has very specific standards for how we should format these kinds of graphs. And there's a few important things you need to consider before you start trying to make one. First of all, if you've already described this data in the written part, you don't need to put in a graph for it. The graph should just be there to supplement your writing. It should be there to provide additional information and some context. So if you've already fully described the data in the text, don't put a graph for it. Another thing that you want to just keep in mind when it comes to creating a graph is it should be as simple as possible. You don't want to have too much information in there. It can easily become overwhelming if it's too cluttered. And one other thing that's very important is your graph should be easy to understand by itself. Somebody should be able to just open up a book, look at your research report, look straight at the graph and figure out what it says. If you have to do all this extra reading just to make sense of a graph, then that's not a good graph. The graph should be able to stand on its own. So here's some technical guidelines from APA. When it comes to your graph's layout, it should be slightly wider than it is tall. So it should be a rectangular layout. The independent variable, if there is one, should always be on the x-axis, and the dependent variable should be on the y-axis. If they're both dependent, like if you're doing a correlation, you know, putting up a scatter plot, then it doesn't really matter which one goes where. But if you have an independent variable, it should go on the x-axis. And values should increase when you go from left to right. So the bottom left corner should always be 0. Well, not always, but in most cases the bottom left corner should be 0, and values should increase from there, both on the y-axis and on the x-axis. A few more guidelines. When it comes to how you make this graph stand on its own, one of the most important things to do is to provide labels. So axis labels should be clear and concise and include the units of measure if they don't appear in like a caption directly below or a brief description directly above the graph. And the whole point of axis labels is just to tell the reader exactly what it is you're presenting here. Now, axis labels should always be parallel to the axis. You don't want to have them at a funny angle. So the y-axis label should be, you know, rotated so that it's like sitting on the line. Same with the x-axis label, it should always be parallel with that line. If you do include a legend, if you need to include a legend, it should appear within the boundaries of the graph. So all I mean by that is, just imagine your graph, you know, this big rectangle, and you have your y-axis here and your x-axis here. The legend should be somewhere in that x and y rectangle that you've made. So the trick though is to try to fit it in there without obscuring any of the data. If that's impossible, then you might have to push it outside of that boundary, but for the most part, you could probably fit it in that boundary somewhere. Now, the text you use for these, you know, axis labels and any other text that you might include in your graph, it should be in the same simple font that you've used throughout your paper. So you don't want to be creative here. You just want to have standardized font style, size, and color throughout the paper. If you do have to use smaller font, it should differ by no more than like 4 points. So try to keep it as similar as possible. A bit more guidelines when it comes to captions. Captions are pretty standard when it comes to graphs. Captions, their intention is to just briefly describe the figure, and they usually come directly after the figure. So you just have this really brief description that explains any abbreviations you may have used and includes a unit of measurement if they don't appear anywhere else. So the caption is just, you know, a clarification for what you've done in your graph. And when it comes to captions in an APA manuscript, those typically are included on a separate page that appears at the end of the manuscript. They just do that kind of thing to make the paper flow a bit better. Like if you want to get that additional information, you can always just go back to that part of the manuscript and read the captions if you'd like. But for APA style research reports, then usually the captions are directly under the graph. And there's different kinds of graphs that you'll see. All these different graphs will typically follow those technical guidelines I was mentioning, but there's many different kinds. So I just briefly wanted to mention a few. Like you have bar graphs, for example. Bar graphs are generally used to present and compare the mean scores for 2 or more groups. Like you might have a bar graph for males and a bar graph for females, and we can look at the 2 bars and see how males and females are different. That's the whole idea of a bar graph. And when we do bar graphs in APA style, the bar, the height of the bar, typically represents the mean score for that group. And then to visualize the standard deviation, we also include something called error bars. So error bars are these smaller vertical bars that extend both upward and downward from the top of the bar to represent the variability in that mean. So the error bars, that's basically a visualization of your standard deviation. Besides bar graphs, we also have line graphs. Line graphs are generally used to present correlations between quantitative variables, similar to scatter plots. But the big difference between a scatter plot and a line graph is line graphs are used when the independent variable has a relatively small number of levels. In other words, we have this y-axis with many different possible values, but the x-axis only has a few possible values, like maybe 3 or 4 or 5 possible values. So that's the big difference between a line graph and a scatter plot. And each point on a line graph represents the mean score on a dependent variable for participants at one level. So it's kind of like you're tracking the participants' progress across time. And that's usually what line graphs are used for. Line graphs are usually used to represent change over time. But for the most part, you can use bar graphs and line graphs interchangeably. All they're really representing, both of these kinds of things, is just means and standard deviations. They both have those error bars I mentioned. The only real difference is line graphs are preferred when you're tracking someone over time. But then there's those scatter plots, which are very similar in those ways I mentioned to a line graph. But the big difference with the scatter plot is that you have numerous possible values on both the x and the y axis. And each point on your scatter plot represents an individual being measured on 2 separate variables. So you're not looking at means here, you're not looking at standard deviations here, you're looking at the raw data for that particular participant at that point. And every single point on your chart is a different person. Now, when it comes to scatter plots, I'm sure you've seen tons of these things before, but when it comes to scatter plots, there's a few other things I just briefly wanted to mention. When the variables you have on your 2 axes, you know, the x-axis and the y-axis, when the variables you have are conceptually similar and measured on the same scale, you should try to emphasize this by making your axes the same length. And that kind of goes against what I was saying earlier about how it should be rectangular shaped, but scatter plots are kind of special in that sense. Like if your x and y are conceptually similar, you should have them be visually similar. Another thing is when you have 2 or more individuals at the exact same spot across these 2 variables, like if you had to put 2 dots right on top of each other, usually we just kind of spread them apart a little bit. So it's not super precise at indicating what their scores were, like we're not putting it at the exact spot that their scores were, but it's the best compromise we can do, you know, just by slightly offsetting them. And then typically what we try to do after we create a scatter plot is something I mentioned previously, which is we try to fit a line on it. We want to try to connect those dots as best as we can. So this, you could call this a line of best fit or whatever, but the whole idea here is we want to try to fit a line on there, and that's typically what you're going to do after you're done making a scatter plot, is you're going to use either your own judgment, or more likely you're going to be using statistical software to try to find that, you know, best fitting line and literally draw it on your scatter plot. So that's all I have to say about graphs. We do have a lot of rules about graphs, and APA style has all this stuff in their textbooks. If you're going to be doing any serious like scientific writing and presenting your writing and research reports, you'll definitely need to get your hand on one of those textbooks. But let's move on. Besides presenting your writing in the text and presenting your results in graphs, there's also tables. Tables are also very common. And the most common use for tables is to present several means and their standard deviations. As you can see down here, this is just an example from APA style as to what an APA style table should look like. And you can see we've got many different conditions, and for each condition there's a mean standard deviation in this table. Like graphs, there are numerous requirements. You know, that APA style textbook I mentioned, it also goes into a lot of detail about tables, such as the inclusion of horizontal lines and where you should put italicized text and stuff like that. So, as I mentioned before, if you are going to be doing any serious scientific writing, you're definitely going to need to get your hand on that APA style guidebook. Another thing you can do with tables, though, is present your data in the form of what's called a correlation matrix. So a correlation matrix is a table that looks like this. It's a table that contains correlation coefficients for every possible combination of two variables that are included in your analysis. So if you look at this correlation matrix, you can see we have correlation, like the number 1 on the y-axis for the table is exactly the same as 1 for the x-axis. So the first correlation it presents is working memory and working memory, and that just gets a horizontal line because it's silly to have a correlation between one thing and itself. But the first meaningful correlation we see is between number 2 executive function and number 1. So we're correlating working memory with executive function, and that gets a very high correlation, as you can see. And then we have processing speed and working memory, and processing speed and executive function. Interestingly, those both get 0.78. And then we have vocabulary and working memory, and vocabulary and executive function, and vocabulary and processing speed, and so on. So you can see how that works. So we're just presenting all these 6 different variables in every possible combination between 2 of them. But when it comes to statistics, especially descriptive statistics, these things can be problematic. They can be problematic to the researcher trying to create them because we have all these rules and standards that you need to follow, but they can also be especially problematic to the reader or the viewer. You know, when you turn on the news, when you go on the internet and you're being shown these charts and graphs and tables, it can easily become overwhelming, and then you can easily be misled. You know, if the researcher fails to properly format their descriptive statistics, then you might come to the wrong conclusions. And this is especially problematic if your viewers, if your readers, aren't too familiar with the topic at hand. But something I want you to understand is, for the most part, people are very skeptical about statistics nowadays because politicians are always putting them out there, and they just seem suspicious all the time. But I want you to understand something. This isn't always intentional. Researchers aren't trying to mislead you. They're trying to present things as factually as they can, for the most part. And when you are being misled by something that's been presented to you, it's much more likely that they just made a mistake. However, it is important to understand how to create these kinds of things so that you can also identify statistics that are of good quality. Like, if you know how to make this kind of stuff as a researcher, then you'll know how to interpret this kind of stuff as a viewer. And you'll be able to notice certain kinds of things. Like, there's basically 3 ways that descriptive statistics can be deceptive, whether intentionally or not. The first one is if a researcher oversimplifies the data, if there's some missing data in there. The second way is if they misrepresent the data, they just don't present it in the way that they should. And the third way, which is unfortunately always intentional, is if the researcher fabricates their data. But that's actually very rare. It's extremely rare for researchers just to create data from nothing. Because if they're caught for doing that, they're in massive trouble. You know, they're not going to get funding for their research anymore. Nobody's going to want to publish their research anymore. They're basically kicked out of the cool group. Like, nobody wants to talk to them. Nobody wants to be their friend anymore because they lied. It's a big, big deal. So most of the time, researchers are far too fearful of the consequences to just straight up fabricate the data. It's much more likely that if they have like nefarious intentions, that they'll just like misrepresent it in some way. So I wanted to just show you a few quick examples of how statistics can be misleading, so that hopefully you'll be a better critic of these statistics that you might see in your everyday life. So consider this one. Just take a moment and look at it. If you just briefly glance at this, you'll see that it's presenting 3 schools and the number of students, and school 3 has the most. Compared to schools 1 and 2, school 3 seems to have a lot more. Okay, so now compare it to this. This is the same story. School 3 has more than 1 and 2. But the thing is these data are exactly the same. This is the exact same data presented to you in 2 different ways. Now you can probably see what I mean by how data can be misrepresented. The data on the right has a very narrow scale on the y-axis, if you didn't notice that, whereas the data on the left has a more appropriate scale. So this would be definitely a pretty clear example of misrepresentation. But like I said, this is usually unintentional. You know, people do this kind of stuff all the time because they want to show you what the differences are, and they just don't think it's important to start at 0. But when you zoom in on those differences like this, it can exaggerate the differences. Here's another example. Just take a moment and look at this real quick. You can see we're comparing drugs A, B, and C, and the number of patients with symptoms went down for all of them at about the same rate. But do you notice the problem here? If you look closely at the x-axis, you'll see it says January, February, March, July. So what happened to April and May? Like, they left out some data. Maybe something really interesting happened in April and May. We don't know because they left it out. They oversimplified the data. Oh yeah, I forgot about June. So April, May, and June. Here's another one. You see that there's these 4 different brands of trucks, and we're comparing them on their functioning after 10 years, but you probably already know what's going on here because we just saw one like this a moment ago. Look at that y-axis. You see it's only looking at the top 5%. If you understand how percent works, it's always out of 100. So it would make a lot more sense for the y-axis to be out of 100. So when you zoom out like this and you look at the data in this more like holistic way, I guess you could say, you can see that those differences are not nearly as big as they looked otherwise. So this again is an example of misrepresentation data. Scale of measurement, in fact, is one of the most common ways that statistics can be misleading, and it is often unintentional. Here's another quick one. This one is titled World Population, 6 regions. You can see Asia, Africa, Europe, South America, Central America, and Middle East. If you haven't noticed the problem here, where's North America? Isn't North America part of the world? It should, if this is about world population, North America should be in there. So this is just another example of oversimplification. And then here's a recent one. This one is titled American Deaths by Disaster. So you have 9/11, Hurricane Katrina, Benghazi, Ebola, Hurricane Maria, and our, present day virus, COVID-19, the coronavirus. And you can see they're comparing these different presidential terms, Bush, Obama, and Trump. Well, if you didn't notice, the scale of the y-axis is completely screwed up. Like, The bar for Benghazi is massive, but it only has a score of 4, whereas the score for COVID is 16,693, but it is minuscule in comparison. Like this chart, if you don't understand how statistics work, this chart is just going to straight up lie to you and mislead you and make you think that Benghazi and Ebola were a much bigger deal in terms of death toll compared to things like Hurricane Katrina or Maria or COVID. But if you know anything, and I hope after watching these videos that you do have the ability to easily notice this kind of stuff. If you do notice, if you do understand anything about statistics, you understand that this is just ridiculous. Whoever made this is just making a joke. They're just trying to be sarcastic. They're one of these cynical people that just likes to poke fun at how uninformed some people can be. So this is intentional misrepresentation just for the sake of a joke. But misrepresentation is not always so funny. When you see stuff like that, it kind of makes you laugh if you know what's going on. But when you see stuff like this, it's not going to make you laugh. And if you understand what's going on, it's going to make you mad. Because this is an example of some very deceptive politics going on, where these politicians are trying to deceive you. They're trying to manipulate you into believing something that simply is not true. So this graph came along with this announcement from Rudy Giuliani, who was, the mayor of New York City. He said that New York City adoptions went up 65% while he was the mayor, and he presented this graph. So if you just take a look at the graph, yeah, it looks like it did go up quite a lot. It's not clear if that's 65%, but it certainly looks like it went up a lot. But if you look at the x-axis, you'll notice that they're grouping years together. You have 1990 to 1995, and then 1996 to 2001. So these are 5-year time periods that they're grouping together. And it would probably make a lot more sense to separate them into a year-by-year basis. But they didn't do that for a good reason. Here's what it would look like if it was a year-by-year basis. You can see the bars in red. That's Rudy Giuliani's term. But wait a minute. If we go back to this one, you see it's 1990 to 1995. 1990 was long before he was the mayor. So what we're comparing in Rudy Giuliani's graph that we just saw is not at all what you thought it was. You thought you were looking at the beginning of Giuliani's term compared to the end of Giuliani's term, when in reality, we're looking at, before he was the mayor compared to the middle of his mayor run. If we wanted to make a more meaningful comparison, if we wanted to do the comparison that Giuliani was implying that he did, then we would want to compare the first half of his time as mayor to the last half. But you can see the data is completely opposite from what he was trying to say. He didn't want to present this data to you because it would have gone against the argument he was trying to make. So that's all I mean. This kind of misrepresentation is intentional. It's very sly. And in fact, it's pretty disgusting. When I see this kind of stuff being put out there on, news broadcasts, it just infuriates me, because I know people are going to believe it. People are going to fall for it. People don't understand what these numbers mean, and it can easily trick people. As a famous author, Mark Twain once said, there's 3 kinds of lies. You have lies, damn lies, and statistics.